Hey guys, we're back with another science lesson, and today we're going to be looking at the phase changes of water and actually doing a real science experiment. So go ahead and get your packets. Join me for the phases of water lab. To get you warmed up, so to speak, our question of the day is, does hot water freeze faster than cold water? This is one of those questions that I've heard a lot, but how do we know if it's true or not? Well, you have to actually do the experiment and give it a try. So, SciShow's done it for you. You can also do this at home quite easily. Get a container of warm water and a container of cold water. Put them in the freezer. There's a couple things you got to be careful about, though. What are the constants? What has to be the same between your two experimental setups? Let's see what SciShow has to say about this.
Experiment has been performed by brilliant people all over the world. And in those experiments, sometimes hot water freezes faster than cold water. And sometimes it doesn't. And either way, the results of the experiment are not reproducible. The observation that hot water will freeze faster than cold water is called the Pumbaa Effect. It's named after Erasto Pumbaa, who noticed the effect in 1963 when he was just 13 years old and making ice cream with his classmates. He noticed that the ice cream mixture made with hot milk froze faster than the mixture made with cold milk. However, he wasn't the first person to make this claim. Aristotle said the same thing in the year 4 BCE. Just, not about ice cream. René Descartes and Francis Bacon also believed that hot water froze faster than cold water. But scientists aren't convinced that the Pumbaa effect is actually a thing. Here's the problem. When you have any two samples of water, that's just ordinary tap water, one of them will always freeze first. And that's because the mixture of impurities in the water will be slightly different. The differences in composition, size, and position of those impurities can make the freezing point of water vary by several degrees. Hot tap water will freeze before cold distilled water if you control for all other conditions, because impurities in the tap water mean that it just freezes at a higher temperature. So in that case, the hot water does freeze first, but not because it's hot. If the Pumbaa effect is a thing and warmer water really does freeze faster, there are a lot of theories for why that might happen. Evaporation is the simplest and probably best one. Some of the hot water will evaporate as it cools, meaning there's just less water to freeze, so it doesn't take as much time. But the Pumbaa effect has been observed while using sealed containers, which prevented evaporated water from escaping. Other researchers who have looked into the Pumbaa effect claim it has to do with convection currents, the way water moves around as it heats, or covalent bonds, or how hot water holds less dissolved gas, which maybe does something. They're not really sure. Want to test it yourself? Stick some water in your freezer.
Well, what did we learn? Well, it seems like you're going to really have to try this for yourself. Even though this has been repeated many times by scientists, maybe just slight variations between the containers is enough to cause the difference. And the thought, the myth, if you will, that hot water freezes faster than cold water. Today we're going to continue on with that theme as we do our Phases of Water Lab. Let's take a quick look at what's coming up. Don't forget your superhero project is coming up due along with liquid mountaineering, both on 11/25. Please make sure you're heading to Schoology and getting both of those things done. Today's question is, using scientific method, can we answer a question such as, what happens to the temperature of water when it freezes? How do we do science? And let's do some data collection. So if you haven't already got your packet out, let's find our Phases of Water Lab, because I'm going to have you guys try to actually solve this question. All right, what are we going to do? We're going to use science to answer a question about what will happen to the temperature of water as it changes from solid to liquid to gas. Now, scientific method definitely wants to make sure that you guys do this in a step-by-step way. First thing we do is define a question that we can answer. We can actually measure the temperature of water as it changes from solid to liquid to gas. When we get the data, we'll have the answer to this question. Before we do it, to make things a little more interesting, why don't we take a vote or a choice, or what we would call make a hypothesis, about this question. I'm going to give you 4 choices to look at. What will happen to the temperature as the water changes? I don't know if you can see me. Okay, starting again. Let's take a look at the 4 choices we have to answer this question. Choice A says the temperature will steadily increase, steadily and smoothly. So our setup is going to involve a container of ice on a hot plate set to full bore. We're going to have the hottest setting we can have. We're going to put our sample of ice in a container. As the time increases, we're going to be watching the temperature. The temperature is going to change. We can hypothesize that it will increase. But how will it increase? In choice A, it's a slow, steady increase. In other words, the longer the sample is on the heat, we can predict that the temperature will increase at a nice steady pace, nice and consistent, as we go from a solid ice to liquid to gas. Choice B says the overall temperature increases, however, there'll be 2 points where the temperature remains constant or does not change. So what we're looking at here is time on the heat adds an increase in temperature to our sample, but suddenly the temperature stops increasing. It stays flat. It'll stay at a certain point for quite a bit of time, and then suddenly it will rise. Then it will be flat, and then it will rise. Kind of like a step pattern. Choice C says the temperature will rise in an increasing or an accelerating rate as the time continues to add up. The temperature will accelerate. It will not rise in a steady manner, nor in steps, but it will just continue to rise faster and faster and faster the longer it's on the sample. And choice D says that as time increases, the temperature rises at a nice constant rate, hits some point where it suddenly drops. Knowing what you know about ice, solids, liquids, and gases, make a prediction. What will happen to our sample of ice on a heater as it changes from a solid to liquid through gas? Choose A, B, C, or D. All right, when we do experiments, what we want to do is try to isolate the variables so that we're only testing one thing at a time. The independent variable in our sample, the one thing that we have control over and the only thing that should actually change is how long your sample is on the heat. So we're going to put a sample on heat, record time every couple of minutes. That's the one variable we are controlling. We don't have control over the dependent variable. The dependent variable depends on, in this case, how long the sample is on the heat. This is what we're going to be measuring. The temperature in Celsius will depend on how long the sample is on the heater. So that's why we call this the dependent variable. These are the two variables that we end up putting together in our graph, and they help us answer our questions. Constants are the things that need to stay the same. If we were to do this experiment 4 times and look at different results, what would need to stay the same between all of our experiments? I can think of a few things. You might want to keep the amount of ice the same that you start with. You might want to keep the type of container the same. For example, a glass container versus a metal container might give you possibly a complete different result. Constants are things that we do to make sure that everything stays fair. Okay? For example, we wouldn't want to turn the heater up full blast, then turn it down, and then turn it up again. Of course, that's going to change the heating rate, and that's going to change the way the temperatures are going to interact. So we're going to keep constant heat. We're going to have only one container, and we're going to have a consistent amount of ice that we test. Go ahead and fill in some constants, some things that you think would keep this experiment fair and balanced so that we would get the actual correct answer. Okay, now it's time for data. So we're going to actually do this experiment for you virtually. Of course, it's something you could do at home. Of course, we're working with hot surfaces, so you're going to need guidance and permission and someone to oversee that, make sure this doesn't get out of control. But what we're going to do is record temperature every 2 minutes. As you can see, we're expecting the temperatures to rise, but we want to know how it's going to rise. So our choices will be A, B, C, and D as far as slow and steady, in steps, and accelerated, or a rise followed by a drop off. And we have room in our data table to take observations. What do we see happening? These can be useful when we later make a claim or we try to answer our question. What happens to the temperature as the sample is heated over time? So due to time constraints, we are going to insert that here. And thanks to the magic of editing, we'll be able to quickly show you results. What I'd like you to do is fill in your data for the temperatures as you watch the ice going through its changes of phase. Okay guys, now here we go with the actual lab. Okay, I have my ice. I have the hot plate here, which is at full bore, and we are looking at the ice being solid at time 0. I'll be recording temperatures and filling in our data table. So I'm going to start the experiment now, and every 2 minutes, and through the magic of editing, we'll be skipping ahead, of course, the minutes, but I'm going to tell you the temperature, and you'll be filling in your table with our data. So I'm starting now at time 0. Okay. At time 0, the temperature of the ice is 0 degrees Celsius. The ice has been out of the freezer for a few minutes, just getting over here, and it is now at 0 degrees Celsius. Okay, so for time 0, I'm going to put my temperature 0. These are all in degrees Celsius. And my observations is I have solid ice just at the melting, at the stage of just beginning to melt. All right, folks, now through the magic of editing, we are now at 2 minutes of time, and I'll be recording the temperature. And I'm not sure if you can visualize that. This is a thermometer that uses just basically infrared, but I can record that temperature. I'm not sure if it's visible to you, but we are at 0 degrees Celsius for the 2-minute mark. We're at 0 degrees. I'm seeing the same result. I'm seeing solid. I am seeing some melt at the bottom, but since I still have solid ice, when I take the temperature of the solid ice, it is at 0 degrees. All right, folks, we're at the 4-minute mark, and as you can see, some of that ice has continued to melt, but I still have solid ice here in my container. So I'm measuring the solid, liquid to gas. So since I still have solid ice, I'm still at the melting temperature, which is 0 degrees Celsius. So I'm seeing more melting, but I'm basically still seeing solid turning to liquid, and you can see the liquid is starting to rise. All right, folks, we are at our 6-minute mark, and I'll take a quick measurement for us. Okay, that is a 0.1, which is close enough to 0. I think that our measurement has not significantly changed. We have solid to melting now, quite a bit more melting. In fact, you might have just seen the ice solid fall down into the liquid. So we are making a nice phase change here. However, the solid part, the ice itself, is still significantly going to remain at about a 0 degree temperature. So I'll see you in 2 minutes for our next measurement. I'm expecting to see quite a bit more melting as we move. All right, ladies and gentlemen, we have our next measurement at 8 minutes, and there's quite a bit of melting. I still do see some solid, but I'm going to try to aim, and it's a little tricky to aim sometimes, this probe at the correct part. I'm trying to hit now the liquid, and I'm at 17 degrees. Now that's Celsius, 17 degrees. So this is my first real big change. You know, I'm looking now at the liquid portion, which is mostly what we have, just tiny bits of ice remaining. So I'm going to say mostly liquid. And I do have the same molecules that I had in the ice. I'm just moving them by adding energy. I've moved them faster. They've moved a little farther apart so that they're able to flow. And from now on in, we're going to be measuring the liquid until that changes into the gas. So we'll see you in a minute or two. And we're back at the 10-minute mark, taking a quick temperature of what's remaining as liquid now. And we are at 43 degrees Celsius. That's 43 degrees. And it is completely liquid, and I don't know if you can see anything inside to indicate any other changes. Material's completely liquid. We're talking about a Celsius measurement, so it's rather warm. 100 is boiling. We're about halfway between freezing and boiling at this point. We'll see you in a minute. Okay, guys, we're back. It's been about another 2 minutes, and I just wanted to let you see the changes here. I've seen, at least from my angle, I don't know if that's visible to you at all, but there is some condensation now on the inside of that, which lets me know that there's some vaporization happening, although it's definitely not at a boil. So we're not completely turned to gas. But my temperature reading now is at 63 Celsius for the 12-minute mark. It is still a liquid, however, I do see some condensation is beginning to form. That is a clue that vaporization will be coming. So we'll see you in a couple minutes and see what's happening. Okay, we're back for our next data point, and I thought maybe we could take a closer look. You can see almost some waves of heat happening through there. There's definitely more motion. The molecules are for sure speeding up, starting to circulate, and a lot more condensation on the inside of that container. If I take a quick measurement, I'm at 82 degrees. 82. So we are definitely seeing another increase in temperature. So let's go back so we can add our data point at 82 degrees Celsius. Starting to see just the beginning of some formation of some small bubbles. Remember, the bottom is significantly warmer than the top, so a little bit of vaporization even happening at the bottom there. It's not a full boil, so we're just going to call that the simmer, the beginning of some vaporization. And we'll see you in a couple minutes. All right, guys, let's take a quick look at where we've gotten to now in just 2 minutes. We definitely have quite a bit of boiling happening. And if I take a quick reading, we're getting interference now even from the steam coming up. So I have to look through the side of the glass, which gives us a reading that's not quite as accurate, but it's pretty close. We're reading 100 degrees Celsius. So let's go ahead and put that into our data table. 100 Celsius. I would call that boiling or vaporizing. And you can see there's plenty of steam being created, even some condensation that's dripping back down into the beaker. So we've got boiling. Let's see what happens in 2 minutes. Does that temperature increase? Welcome back. Let's take a quick look. After 2 minutes, things look very similar. We've got a lot of boiling. Maybe a little bit of the water is actually boiled out of the container into the gas. Hard to see above, but there's steam rising up. Take a quick temperature reading from the side. And would you expect that temperature to rise? Let's take a quick look. And trying to hit just the water, not the container. Aha, there we are. 100 degrees Celsius. Let's add that to our data point. We are at 100 degrees. I'm going to say continues to boil. And we'll be back in 2 minutes to see what our final data point will reveal. Welcome back, guys. We're at our final data point, just so we can take another quick look. The water remains boiling. There is still a lot of vaporization. And our temperature reading is remaining constant. We are still at 100 degrees Celsius, which is kind of the expected number, as that is the boiling point of water. And it continues to boil. So let's take a quick look at our data. We've got the water starting as a frozen solid of ice, remaining at 0 degrees Celsius for 6 minutes until the ice fell into the liquid. And from there on, our liquid temperature rose by increments of about 20 degrees until we got to this 100 boiling point, at which time the temperature stayed constant again. So that is data. If you don't have that, please make sure you get that written down into your data table. All right, guys, so now you've seen the actual experiment. Let's take a look at what we're going to do with this. We're going to analyze this data. So to do that in a meaningful way, what you'd like to do is make a graph. And when you graph this data, our dependent variable, which is temperature, will be on the y-axis. The y-axis is this up and down column here, and our time is the independent variable that will go on what we call the x-axis. So go ahead and set up your graph similar to this. The title could be about phase change or change of state of water. So we've got temperature, degrees Celsius, and time. So I've got the graph set up for you, which you can continue these numbers. We've got 0 time, 2 minutes, 4. I've skipped every other line just to space things out, going 8, 10, all the way to 20 of my temperature. I know it's 0, but I put a -10 just in case we had a lower temperature. We didn't. We started at 0. and I counted by tens, and you can continue counting by tens all the way to 100 somewhere up at the top. So pause the video, take a few minutes to at least set up the axes of your graph, and then we can add different data points and see exactly which choice, A, B, C, or D, matches up with the actual data. So I'm looking at my 4 choices that we started with. What happens to the temperature of water? What was your prediction? Slow and steady increase, a stepwise increase, an acceleration, or a drop-off? Well, I definitely didn't see a drop-off. I definitely did see temperatures rising. Were they slow and steady, accelerating, or in the form of steps? To find out, we're going to have to add our data points to our graph, connect the dots, and make a line. All right, guys, welcome back. Now we're going to go ahead and analyze this data. And if you're not sure about graphs and you're not sure where I got these dots, let me show you exactly where all this is coming from. We're going to go to our data table, and we're going to put a dot for each of these data points. Let's start with our first one. When the time is 0, our temperature is 0. So how does that look on a graph? First, I need to find the time when it's 0. That's right here. The temperature at 0 is here. Where those 2 lines intersect, I put a dot right there. That's my first data point. My second data point comes from time at 2 minutes. 2 minutes, and I have 0 degrees change. So there's the dot for the 2-minute mark. At 4 minutes, I need to go back and find out what my data says. 0 degrees, which is this line here. At 6 minutes, I also have 0 degrees. The only change happens at 8 minutes, where it's 17 degrees. 8 minutes occurs here, and of course I want to fill in the rest of the points on this axis so I know exactly where they are. The way I did it, I skipped every other line. 17 degrees fits about here, right? Between 10 and 20, closer to 20. That's a good approximation of that data point. Try to get it on the line as best you can. And then we're going to keep continuing plotting all of our points. Then you simply draw a line to connect the points and see what you get when you connect all the dots. That's how we make a line graph. Next, you can go to our question. What happens to the temperature of water as it changes state? Which of these 4 choices matches best with your graph? Final thing to do, guys, is to do a conclusion. In science, we're going to make a claim, provide evidence, and give a reason. The claim is a 1-sentence answer to the question that we started with. What happens to the temperature of water when it changes state? Look at the graph you made and put that change of temperature into words. Evidence means I'm going to give information. So I'm going to use something from my data table or graph to explain what's going on. So you could even say something as specific as from 0 minutes to 6 minutes, the temperature was 0. However, from 8 minutes to 14 minutes, what happened? I could tell the increase. You could subtract 82 minus 17 to find the exact number if you like. Finally, we're going to give a reason. This is usually the most difficult part. What's your reason for the claim you made? Why does water do what it does? Okay. You may have to go back to your notes. You may have to research a little bit. Research is part of the scientific method after all. Why does the graph you made happen? And spoilers, guys, this graph that you made would work for chocolate, gold, water, or any pure material. So, once you've done your claim, evidence, and reasoning, you have now done a complete science experiment to answer this question. Way to go. Thanks so much. Hopefully that made sense to you guys, and you can go ahead and finish up everything and submit to Schoology. Congratulations, and thanks for trying science. See you next time.